Okay, the learning objectives for this segment are going to be, we're going to dig a little bit into the math when we start out and actually connect the math of the Schrödinger equation to the shapes of the orbitals that we see. Count the numbers of electrons in orbitals, shells, and subshells, including spins. Understand the reasons for differences between hydrogen orbitals and other atoms. And yeah, so what I'm going to do now is actually show you the solutions to Schrödinger's equation. So the hydrogen atom is spherically symmetric. So it's easier to describe locations around this atom rather than in terms of x, y, and z coordinates because which direction is x, which is y. Nature doesn't care. In terms of distance from the center and then angles in either direction from, once you're at a distance from the atom, angles from some reference point. So at least for n equals 1, 2, and 3, you can break it down as a function that's a product in two angles. That's the f function that's a product of an angle, the p function, and a radial function. For more complex, it starts to get a little weirder, and you actually you have a combined a y function that includes both of the angles, but you still have a radial component as well. So the energy of a solution to Schrödinger's equation is of the form me, that's mass of electrons, times the charge of the electron to the fourth, that's this e here, it's not an exponentially, it's the charge of the electron, times 8. This E0 squared is the constant that has to do with the dielectric permittivity of space. It just has, basically it's related to the strength of the Coulomb interaction. Planck's constant squared times n squared. So all of this is just a bunch of constants that don't depend on the particular orbitals. What does matter here is this n squared. So it's a constant over n squared. Does this look familiar? Yeah, energies are proportional. Differences between energy levels are proportional to some constant times 1 over n squared. So if we were to just subtract two energy levels, we get something that looks like a constant over n squared minus m squared minus the same constant over n squared. Does that, and that would be our energy difference, right? So that is exactly what Rydberg observed. So once you plug in Schrödinger's equation, you get out immediately that the energy levels are, that's really hard to read there. You would get some constant, let's switch to, our delta E equals some constant that has to do with the mass of the electron, all of that, over m squared minus the same constant over n squared. And that turns precisely into Rydberg's equation. Yeah, so you plop the math and you solve the math that comes out of Schrödinger's equation. It tells you, yeah, here we go. The energy levels are going to be some constant times this different m's and n's. I remember delta E is proportional to the frequency, which is 1 over the wavelength. So it's all completely internally mathematically consistent. A couple other constants here. This A0 is h bar squared. Remember, h bar is Planck's constant divided by 2m divided by the mass of the electron times electron charge squared. It turns out that has units of distance if you take a look at it. And so that ends up being sort of a reference distance for, sets a distance scale for the atom. Notice this number right here. That's the maximum in a 1s orbital of where you find the density. So that number, that distance comes straight out of sort of fundamental constants of nature. Okay, for n equals 1, L equals 1, ML is 0. Notice there's no dependence on the angles here, but there is this exponential. It's basically just an exponential. It's an exponential times a constant, exponential decay. For the 2's, notice there's no angle dependence here, no angle dependence here. But now we have something more complicated. We have something that crosses the line, like where this is 0, this can be 0, where 2 equals r over a 0. In other words, r equals to a 0. We get a node. So there's a node. Where's the node? It's a 2a0, which you can read straight off of Schrödinger's equation. It's where this thing is 0. It's the only thing that can be 0. And now we've got an exponential factor. How fast does it decay off? Now we're dividing by 2a0. Why? Because it's n equals 2. And now if you notice the 2p electrons, now they have a slightly different angular dependence. They don't have a node here. Will this, no? Auto minimize. There we go. They have a simpler angular dependence. There is no radial node here. Like r is always positive. Exponential something is always positive. So there's no nodes here, no nodes in r, but you do have these sines and cosines terms. And if you're careful with the sines and cosines, you can see that, yeah, that gives you pxy, p and x, y, and z. So just by looking, so these are like kind of nasty equations, but they're not super nasty. Like you can write them out all on one page. Let's go to the next page. So now here we've got all of the 3 electrons. We've got 3s. 3s has 3s, it's s. So no angular dependence here, just constants. And now we've got, instead of a linear term, we've got a quadratic term. A quadratic term has 2 solutions, 2 places where it crosses the line. And so we get 2 nodes here because it's quadratic. Here in the 2p, we have 1 node in r, and then we have our sines and cosine terms. And our d's have no radial nodes. There's no radial nodes there. Their characteristic distance of all of these have the exponential factor of 3a0 because they have a characteristic distance of 3 times this a0. And now if you notice, these are just simple sines and cosines. Here you start getting wackier functions of sines and cosines. And that's what gives the d orbitals their 4-lobe shape. So you can keep going with this process. We will not do so. That is just too painful. But all the wacky pictures we saw in that demo have this pattern. Some polynomial of sines and cosines of the 2 angles, and some polynomial times an exponential of the radial function. And wacky constants here to get everything to integrate out so the probability is 1 everywhere. They just get more and more complicated, but they're all of this pattern. These are knowable things, like you know how to write functions that are sums of exponentials, polynomials, and trig, right? These just happen to be combinations that describe how electrons behave around protons in all atoms. So although it's complicated, it's really amazing that all of the chemical behavior comes out of solving one equation that you write down and then just turning the crank to get all the solutions of the equation. So as complicated as it is, I just want to point out that, for something that explains absolutely everything in chemistry, it ain't bad at all in terms of complexity. This is a knowable amount of complexity. You wouldn't want to learn this all now, but in a physical chemistry class, you'll actually, depending on how rigorous the teacher is, they might make you actually prove that some of these are solutions to Schrödinger's equation. But this is knowable stuff that you can learn as an undergrad, but let's not learn any more about this at this time. Just a taste to see what's going on. Okay, cool. So that is how the actual math of Schrödinger equations matches the pictures that we saw.